Our next speaker is professor at Pratt Institute. He's an architect, a futurist, and widely known in his community of design ideas. I'd like to welcome John Lobell.
Thank you. So I want to thank Natasha and high tech here. Let's see if I can time this stuff. Thank Natasha and Ed and everybody else here. I'm an architect, so I appreciated Francois' talk, and so we make things. So I'm thinking about making things, and here's a question. If you wanted to make an oak tree, you would not start with a telephone pole, nail some sticks to it, glue some leaves to the stick. You would sprinkle some rules on the ground, an acorn, and let it make itself. Why aren't we making our cell phones that way? So, is this possible? So, 1953, Watson and Crick crack DNA, and 4 letters, 2 rules, and you can make all of life. So that's pretty helpful for, hey, maybe we could make things. Here's the spider goat. They still really aren't happy with trying to get the stuff out of the milk. But spider silk is very strong. Spiders don't like to be herded and milked. So you take spider DNA, put it into a goat, and it just churns out the silk proteins in the milk. We all following the news from Craig Venter as they continually get closer to making life. But 1953, same year as Watson and Crick, John von Neumann at the Princeton Institute said to Stanislav Holm, how would you make a machine that could reproduce itself? And Holmes said, well, have you played with cellular automata? They pursued 2 lines of thought. One was cellular automata, which is, for us today, doing it in the computer, and the other is doing it in real life. And Neumann envisioned a whole sea of parts and barges that would float around and collect them. And 1970, Conway developed Game of Life. So this thing here is manufacturing these guys. If this was a little animation, you see these little colliders coming off of here. So this manufactures those guys. So we can actually, maybe we can make these things. We're familiar with Wolfram and his 256 one-dimensional cellular automata. And Wolfram says, I think when I find the code that generates our world, it'll be just 6 lines. So the code to make things could be very simple. L systems, this fern here is generated by a Lindenmere system. It is so convincing that, hey, it's obvious nature is using that system in a lot of cases. We're all familiar with this, and now, and we can do that literally infinitely. In other words, this extremely simple formula can make infinite complexity as we zoom in on our Mandelbrot set. This is a 3-dimensional Mandelbrot set. You can do this in 3D. You're not limited to 2D. So, can we use these principles of simple genomic rules to make things? We're getting there. One problem is we're still in the computer, so we've got to get out of the computer. Tinkercell, that's also in the computer, but you can get, just the way my students work with CAD to make things, Tinkercell enables you to, it gives you cells, membranes, enzymes, genes, and you can, manufacture life in your computer. can we get this out of the computer? So two of the heroes for the cryonics people, Robert cryonics and nanotechnology. Robert Freitas, he's the pioneer in those little nanorobots that are going to go into your bloodstream and clean out the plaque. And Ralph Merkel, you look him up on Wikipedia, he's one of the creators of public key, private key encryption, but he's big into nanotechnology. He did a book called Kinematic, which means real physical in the world as opposed to in computers, self-replicating machines. Fantastic book. You really should have it. This is sort of a diagram of the history of the field. They have a massive patent. I printed it out. It's about that thick. So all future manufacturing is going to be done this way. These guys are going to own it. Here's Neil Gershenfeld going to Africa with a big box that can make anything. So the way we do 3D printing, he can do 3D manufacturing. It has feeders of chips in it. So you can make a cell phone. You don't make the chip. There are feeder chips in there. But the Fab Lab at MIT can make anything. Forgot to tell this thing not to shut off. This is a replicant. This is a machine that can make itself. Now, this is a little video that the nanotech people made, and you can watch it manufacture a laptop computer with 1 billion processors. But it looks like a giant 19th century factory miniaturized. I'm not sure it's going to be done that way. This is IBM using self-assembly to make chips. In other words, when we start using carbon nanotubes to make chips, we're not going to be using tiny tweezers to make the circuits. And you can't do it photographically, which is how we do it in silicon. How are we going to make them? Well, IBM's getting them to assemble themselves. So a couple of my colleagues, architects who've been interested in these ideas. This is Elisa Andrzak bio thing, and she generates the rules. These things make themselves in the computer, and then these are just 3D printed. Elena Montefiore is very interested in fashion as well as growing buildings. Jonas Casimir, very, very strong biological analogies. William McDonald, chair of the graduate department of architecture of Pratt, has developed this wall. It's going up on some buildings now that's got, does the heating and the solar and checks rainwater and does the whole thing. David Rue, this really cool stuff. Growing this stuff in the computer and then printing it. Peter McApia, he uses swarming algorithms to develop his architecture. Now, this is the most interesting one, Carl Schuh, and he gives his students 3 genes, A, B, and C, and by the end of the semester, they have grown their buildings. And, be a whole lecture just to show how they do that. But this is another colleague of mine, Haresh Lalvani, and he works in 27 dimensions, and he's working on mapping the morphological genome, the underlying principle of all form, human-made and natural-made, and he can navigate from any form to any other form, and as you move along that line, you morph from one form to the next. And these guys here, he actually produced, he started with polyhedrons and was working at that lab at New York Institute of Technology, and George Lucas stole the whole team, and they found Pixar, and they were working with polyhedrons. Gives numbers to these forms to morph from one into another. These are ones we've actually fabricated in titanium. These are the Permanent Collection Museum of Modern Art. This is stuff he's doing now. And we're actually trying to, this stuff is made, the way you make metal, but we're using processes that are starting to have implications for this self-fabrication idea. see interesting geometric things going on, and these things deform and generate these different geometries. He did an apartment building, and then the economy fell out from under him before we could get it underway. This is a company Suresh works out. I work there also. This is my website, Genomics. Let me go there. This guy's making these little gliders. Here's my contact information, and thank you.